Welcome, everybody. My name is Jessica Chu, and I am a member of the ICCT's communications team. Thank you for joining us today. Our webinar will cover the real-world performance of electric vehicles in China and all about the energy consumption, range, and charging patterns. Today's presentation will last approximately 25 minutes, and afterwards, we will have an additional 5 minutes for questions and discussion. The total webinar will last about half an hour, so you can plan your time accordingly. Before we begin, I have a couple of housekeeping items to address. First of all, the webinar is now being recorded, and everyone's microphone is currently on mute. Second, if you have questions about the presentation, please write them in the question blog in the control panel, and that's at the bottom of your screen. And we will be collecting these throughout the presentation and answer them during the Q&A session. Lastly, today's webinar will be presented by ICCT's researchers Lingzhi and Shiyue. So without further ado, let's welcome our presenters. And Lingzhi, the floor is all yours.
Thanks, Jessica. Hi, everyone. I'm Lingzhi. I, together with my colleague, Shiyue, today will present to you on the topic of real-world performance of electric vehicles in China, energy consumption, range, and charging patterns. So first, some background. Electric vehicles, or EVs, are expected to play an important role in helping to deliver on China's national decarbonization commitment, which were first announced at the United Nations General Assembly in September 2020. One of the consumer concerns in China on EV is their real-world range was less than that indicated by the nominal values. The nominal values are from the type approval certification process, and these are reported publicly by the automakers and the Ministry of Industry and Information Technology of China. In this project, we collaborated with the Open Lab of National Big Data Alliance of New Energy Vehicles, or NDA-NEV, to better understand this difference. The Open Lab of the NDA-NEV is an organization that aims to better monitor and manage the operation of NEVs. It has been in operation since the beginning of 2017, and the total number of vehicles connected to it exceeds 9 million, which is about 90% of China's NEV stock, and total mileage of over 300 billion kilometers was recorded by July 2020. Vehicles usually upload operation data every 30 seconds, and raw data includes status, speed, accumulated mileage, current, voltage, state of charge, and more. With our two reports, one on passenger car and one on heavy-duty vehicles, we aim to offer a range of stakeholders analysis of the real-world performance and use pattern of battery electric vehicles based on a large set of real-world data. So first, I would introduce the part on battery electric passenger cars, and my colleague Shiyue will talk about battery electric heavy-duty vehicles. So first, let's look at the scope of this analysis. We identified 10 best-selling battery passenger car models in China during the period from 2017 to the end of 2021. And the vehicle operations data that we analyzed is from 2021. We only included private use cars of those 10 models that were registered in 5 selected cities in 2021. And these 5 cities are Shenyang, Beijing, Hangzhou, Chengdu, and Guangzhou. And they have different climates. This yielded a total data set of over 140,000 vehicles. So this figure shows real-world energy consumption under different driving conditions by model on the top and city at the bottom. Definitions of these conditions are shown in the legend, represented as points of different colors. Nominal value for each model is shown as the yellow line. We see that the impact from these conditions follow a similar pattern across cities and models. Low ambient temperature had the most adverse impact on energy consumption among the real-world conditions we analyzed. The increase in energy consumption in very cold conditions, which is at or below -7 degrees Celsius ambient temperature, ranged from 40% to 90% in Shenyang and Beijing. These two cities have the coldest average temperature in winter among the 5 selected cities. And when we look at cold conditions, which is at or below 0 degrees Celsius ambient temperature, the increase in energy consumption in cold conditions was found to range from 35% to 75% in Shenyang, compared to nominal values. For a city like Hangzhou, which tends to have slightly higher winter temperature, the increase in energy consumption across models was found to be up to 50%. We also compare energy consumption under the same set of real-world driving conditions by model, but aggregated across all cities. Also, the y-axis is now percent difference from nominal energy consumption, where nominal is shown as the yellow line at 0%. You can see more clearly in this figure that low ambient temperature, illustrated by the light and dark blue points, has the most adverse impact on energy consumption. The increase in energy consumption compared to nominal values is up to 90% in very cold conditions and up to 65% in cold conditions by model. This is followed by high-speed conditions, which increases energy consumption by 20 to 35%. High speed is defined as average driving speed of a trip at above 90 km per hour. In hot conditions, which is 30 to 35 degrees Celsius ambient temperature, the impact is less significant and the increase is within 20%. Here, we translate the increase in energy consumption to reduced electric range. I wanted to specifically point to the data points for all conditions, represented by the dark gray color. They incorporate all operation data, regardless of city, temperature, or speed. Under all conditions, electric range was lower than nominal values across these 10 models except car 1, and average reduction in range was 15%. As already reflected in energy consumption, low ambient temperature had the most adverse impact on range. The reduction in range varied from 30 to 50% in very cold conditions and from 20 to 40% in cold conditions. The reduced range from high-speed driving was between 15% and 25%. High ambient temperature both increased and decreased average range, and its impact was less significant than low ambient temperature or high-speed driving. High temperature increased range by 5% for one model, but generally reduced it up to 15%, likely due to the use of air conditioning. For the same model, real-world electric range varied substantially by city due to factors, including but not limited to climate, topography, and driving style. This figure looks similar to previous ones, but we use color to represent different cities. For example, the range of car 4 was lowest in Shenyang and highest in Guangzhou at 20% and 5% lower than its nominal values. Models with a shorter range and smaller size showed less variance, and this was the case for car 1, 7, and 10, all of which are city cars or microcars. One potential reason for this is that they're typically used in a relatively fixed setting, the daily commute to and from work. In this study, we also looked at charging patterns in addition to energy consumption and range. The figure on the left here shows the share of charging events by the fast versus slow charger, and on the right, the installed public charger by these two charger types. Guangzhou, Hangzhou, and Chengdu saw the highest utilization of fast charger in terms of total number of charging events. One of the factors that contribute to this is that more than half of the installed public chargers in the cities are fast chargers. Almost all of Shenyang's public chargers are fast chargers, but the total number is low compared to other cities, and most of the charging was with slow charger, most likely home chargers. Looking at the share of fast charger on these two figures, except Guangzhou, the share of installed public fast charger is higher than the share of fast charging events, because people also use non-public chargers and many of them are slow chargers. In the case of Guangzhou, the greater reliance on public chargers might indicate that EV drivers prefer fast charger or that they have less access to private chargers. In addition to the number of public chargers, here we also look at how nominal range, shown on the x-axis, is linked to utilization of fast and slow chargers. Car 1 and 10, which are city cars, were exclusively charged using slow chargers, as indicated by their high Y values. Recall that these vehicles have a shorter range and are typically used mainly for daily commute. As the daily use is limited, they're more conveniently charged at home with a slow charger. At the same time, cars 2 and 4, which have the longest range of the selected models, were also mainly charged with slow chargers. This is likely because drivers do not experience much range anxiety and thus charge at the end of the day at home or use public or workplace slow chargers when available. Together with the last slide, we see that the prevalence of public charger type and vehicle range both appear to contribute to drivers' decisions about which type of charger to use. After investigating consumer choice on charger type, we analyzed at which SOC people usually start and end charging events. SOC, or state of charge, is the level of charge of an electric battery relative to its capacity. This is a Sankey diagram showing the flow of the starting SOC and ending SOC of charging events. Starting SOC is on the left and ending SOC is on the right. Each side represents the share of charging events starting or ending with a specific SOC bin, adding up to 100%. The width of lines is proportional to the number of events. We can see that SOC at the start of charging events was distributed largely evenly between 10% and 70%. For over 70% of the events, the ending SOC was between 90% and 100%. Moreover, around 10% of charging events happened at an SOC of over 70%. This suggests that vehicle drivers might have had range anxiety and were charging whenever a charger was available, regardless of SOC, and kept charging until the battery was full or almost fully charged. Next, we analyzed when charging events took place and their duration. And for this, we included both private cars and taxis as a comparison. Overnight charging is defined as an event spanning across midnight. Highest frequency is defined as above 99% quantile of count of event. The charging pattern of private cars is more dispersed than it is for taxis. As you can see, there are more thinner lines on the right and left half of the circle for private cars, which reflects a variety of overnight charging and some likely workplace or public charging during the day. This could be because private use drivers are charging when there is an opportunity, and that is likely to be at least partially reflective of range anxiety. This can be understood as a kind of opportunity charging on the part of private use drivers, and it is usually less than 2 hours before the car is fully charged or has reached the SOC limit that the driver set. There are also similarities between the private car and taxi. For example, many drivers choose to charge during lunch hours. For private cars, another time when charging was frequent was between 3 p.m. and 7 p.m., when many people are done with their workday. For taxis, there was frequent charging during an afternoon peak from 2 to 5 p.m. As the change between the two shifts or drivers usually happens around 6 p.m., this is likely due to the need to charge up after a day's driving and before another driver's shift. Time of use rates could help balance loads at different times of the day. So next, I will pass it off to my colleague Shiyue to introduce the battery electric heavy-duty vehicles.
Yeah, okay, thank you, Lingzhi. Hi, everyone. This is Shiyue, an associate researcher from ICCT. And today, I would like to share with you the second part of our study, the real-world performance of electric heavy-duty vehicles. Yes, please. Next. Yeah. Similar to our study about the passenger vehicles that Lingzhi has introduced, we also identified a group of representative cities across China and collected real-world performance information with our partner. We finally have 18 cities and 9 vehicle categories of heavy-duty vehicles, which covers the most important categories in our daily life, right? This map just shows the layout of the cities in this study. Yes, please. Next one. This figure just shows that a pattern of the electric ranges from different cities for each category. You can find that on the right, as I mentioned, there are 9 categories. For each, we collected the data from 3 cities with different climate conditions. The dashed lines indicate that the nominal ranges and the dots are the real-world values. The first insight from our study is that generally the real-world electric ranges are about 30% shorter than their nominal ranges suggest. The nominal ranges are worked out throughout a test procedure in the lab, which can also be regarded as an official value when one vehicle model to be released. Such a gap is a big gap and may mislead the fleet owners well. The second insight that we can find that for each category, the variance between the cities is somehow fixed, no more than 10%, which implies that the climate and the terrain conditions as a standalone parameter may not be a very big deal for fleet operators. Okay, next one, please. Okay, so this slide also shows just something interesting regarding charging. Another interesting finding of this is that the fleet operators used to apply a very conservative charging strategy in real-world operations due to range anxiety. This figure just shows the pattern of the charging rate and the charging duration, which is shown on the vertical and on the horizontal axis. It seems that the figure just shows that you can find that there's a red curve just indicates that a model to be charged from empty to be fully charged. It seems that actually very few electric heavy-duty vehicles to be actually charged from somehow empty, right? Another finding just regarding the figure is that the fast and the super fast charging, which means the C rate over one is not yet commonly available. That's something interesting new from our study. Okay, next one, please. This slide shows that a Sankey diagram just showing the charging start and the termination level. One particular interesting pattern is that the fleet operators just prefer to charge the electric heavy-duty vehicles to fully charged. We can find that there are about 78% of the charging events just terminated with almost fully charged. And for about like half cases, the charging events just start from 30% to 60% of the SOC. So this we can also have an implication from this pattern is that the fleet operators just charge whenever possible to make sure that their electric heavy-duty vehicles are feasible, are available enough to support their daily operations. Okay, the next one, please. Okay, this figure is also similar to the passenger vehicle side. This figure just shows the time of charging in a day. You can find that the red band just illustrates the overnight charging activities, and the blue band just shows the most frequent charging activities. We can find that the most popular charging time to be about 10 p.m. to 11 p.m., the midnight, and the lunch break, right? So the overnight charging lasts for about 3 to 4 hours. Daytime charging typically just finished within 1 hour. This also somehow that's reasonable to out of our intuitiveness, right? So this pattern also implies that the depot charging still be very, very important and critical for the fleet to own their own electric heavy-duty vehicles in reality. Also, okay, next one, please. Okay, so based on these information that I just introduced above, we can have a quick wrap up. By having the insights mentioned above, that here are some policy opportunities and recommendations for policymakers that can do. First, the policymakers can include realistic and representative test procedures that better reflect real-world performance, which includes high-speed driving, air conditioning use, and extending the procedure to include high and low ambient temperature. That's very important to include all these complex conditions in the test procedure to narrow the gap between real world and the nominal ranges. Second, we suggest to incorporate efficiency and range values under the real world driving conditions in vehicle efficiency labels for consumers. That's something new, but also important for customers to learn the details and available ranges that electric heavy-duty vehicles and passenger vehicles to drive, right? And the third, we also recommend to incentivize with time-varying tariffs to support operations and shift electricity demand to the times of day when the overall demand is lower. This can also help the electric vehicles to reach a competitive level as diesel counterparts as soon as possible. Finally, we still encourage in continued development in charging infrastructure, and I believe that's also something that governments around the world are doing these years. Right. Okay, so that's something from my part. Next one, I suppose that's the end one. Yeah, if you are also interested in more details, just we can just please reach out to us, and you can find that reports on our website. Also, you can just scan the QR code here for our WeChat for more details. So thank you so much. I'll pass to Lingzhi as well.
Thanks, Shiyue. So as we wrap up our presentation, we're now moving on to Q&A. So I can start. There's a question asking what the current test procedure is like regarding temperature. So I can speak in terms of light-duty vehicles. So in China, the range and energy efficiency we see are tested under a moderate temperature of around 23 degrees Celsius. The current test procedure for energy consumption and range of electric light-duty vehicles in China includes methods for testing with air conditioning use under hot and cold temperatures, which extends to 30 and -7 degrees Celsius, but only for information purposes in the appendix, and such testing is not mandatory. But there are such extended temperature ranges in other vehicle regulations. For example, emission standards in the EU and China. For example, light-duty China 6 standard emission standard introduced the low temperature RDE test requirement that has extended temperature up to 35 and down to -7 degrees Celsius. Shiyue, do you see any questions on your side?
Okay, yes, I just also find one from my to me that say why the fleet operators pick the strategy of charging whenever possible instead of the overnight charging. Yeah, that's a very interesting question, because actually that's a reflection of the range anxiety from the operators actually in the real world performance that we can find. That's a very conservative strategy that the operators have to apply with. We can identify that operators want to keep the battery, the SOC of battery, over a more sustainable and comfortable level to make sure that the trucks and the buses are always feasible for a new round of work, right? So that's why, due to this reason, we can also find that most charging activities happen over 30% of the SOC. While in a very few cases that the e-trucks and the buses can be charged under a very limited level, say just under 10%, for example. So that's my answer. Yeah. Thank you. Okay.
Thanks.
Yeah.
Yeah, I think we might have time for one more question. I'm seeing one, and I can also take this. So it's asking like what kind of rural performance information can consumers usually get publicly in China or elsewhere? So this might vary depending on different countries and regions. We did some analysis a while back looking into this for different major markets, and it suggests that consumers have a better chance getting rural range and energy consumption values from automotive websites and nonprofit websites than from OEMs or governments. On the other hand, OEMs might provide more information on things like charging infrastructure and charging time. In China, third-party websites are a major source of information for rural range. There are third-party auto websites in the US as well that do EV range testing and publish those results. In some European countries, as far as I know, some NGOs like the EV database also provide such information. As we mentioned in the key takeaways, if governments can include additional test procedures that better reflect rural performance and include the results in vehicle labels, it will help narrow the gap between nominal values and rural values and ease consumers' concern. I think we're at time, so I'll pass it back to Jessica.
All right, thank you, Lingzhi and Shiyue. We would like to thank everyone for participating in today's webinar. If we did not get to your question, we might follow up with you individually. Please don't hesitate to reach out to us if you have any further questions. You can see Lingzhi and Shiyue's contact information on the screen here. And then our webinar recording will be shared on the website and YouTube channel shortly. So please be sure to check that out. Remember to follow us on social media and subscribe to our newsletters. Our handle is @THEICCT. And if you look on the screen, just like Shiyue mentioned earlier, there is a QR code that links to our WeChat account, and you can find details of ICCT's work in China over there. Lastly, thanks again, and we hope to see you soon. Have a good rest of your day, and we will see you next time. Bye for now. Thank you.
Thank you. Bye-bye.
Bye.